93 billion light years. That's how far we can see in any direction. But here's what keeps physicists awake that might be less than 1% of the actual universe, or 0% if space goes on forever, because there's growing evidence that our entire universe could be just one bubble floating in something incomprehensibly larger. A multiverse where the laws of physics themselves change from bubble to bubble. So we're going to start at the edge of what we can see and then watch as every assumption quietly falls apart. I'd be grateful if you'd subscribe and softly support the video. The observable universe has a radius of 46.5 billion light years. Not because space ends there, but because light from farther away hasn't had time to reach us yet. The Big Bang happened 13.8 billion years ago, and while photons have been racing toward Earth ever since space itself has been expanding, by the time those ancient photons arrive, their source galaxies have been pushed much farther away. The result is a sphere centered on Earth. Everything inside that sphere is in principle observable. Everything outside is not and never will be. Every second, 20,000 galaxies cross that boundary. The space between us and them expands faster than light can travel through it, which means their photons will never close the gap, not in a billion years, not in a trillion. Those galaxies still exist, stars still burn, planets still orbit, but we've lost them permanently. This isn't some far future problem. It's happening now while you're listening to this. The observable universe is shrinking in terms of what we'll eventually be able to see, even as space itself expands. But the critical question isn't what we've lost, it's what was never visible to begin with. In 2023, the European Space Agency published refined data from the Planck satellite, which spent years mapping the cosmic microwave background, the faint radiation left over from the Big Bang. Planck measured the curvature of space with unprecedented precision. The result, the universe is flat to within 0.4%. That single measurement has enormous implications. In Einstein's general relativity, the shape of space determines whether the universe is finite or infinite. A universe that curves like a sphere is closed and finite. A universe that curves like a saddle is open but still bounded in a complex way. But a flat universe, a universe with zero curvature, can extend forever. And the data says flat, which leaves two possibilities. Either the universe truly is infinite, stretching endlessly in all directions, or it's so large that any curvature is undetectable. If it's the latter, the math is brutal. For the curvature to be below Planck's measurement threshold, the full universe would need to be at least 250 times wider than the observable portion. 250 times 93 billion light-years is 23,250 billion light-years. Every galaxy ever photographed, every quasar, every nebula, every black hole, all of it combined, represents less than 0.5% of what exists. But if the universe is perfectly flat and the data keeps pointing that way, then 250 times is meaningless. The universe isn't just bigger than we thought. It's infinitely bigger. No edge, no center, no boundary where space transitions into something else. Just galaxies and voids continuing in every direction without end. The Planck data isn't some outlier. In 2024, observations from the James Webb Space Telescope confirmed the same flat geometry. Galaxies at the edge of visibility, their light redshifted by 13 billion years of expansion, matched the predictions of a flat universe almost exactly. No deviation, no hint of curvature. Space doesn't curve back on itself. It just keeps going. Which raises an uncomfortable question: if we can only see a tiny bubble within something vastly larger or infinite, what's out there in the rest of it? Is it more of the same? More galaxies, more stars, more hydrogen clouds collapsing into white suns. Statistically, if the universe is infinite and uniform, then everything that can happen does happen. Somewhere out there, far beyond the horizon, there's another Earth, another you, another version of this exact moment, but with one detail changed, and another, and another. Infinite variations all playing out simultaneously, in regions of space we'll never contact. Or maybe it's not uniform. Maybe the laws of physics shift beyond the horizon. Maybe the constants drift gravity a little stronger here, electromagnetism a little weaker there. Maybe matter behaves in ways we'd never recognize, forming structures that have no analog in our observable patch. We have no way to know. The horizon is absolute. Light can't outrun the expansion of space. No signal, no particle, no information of any kind can cross that boundary and reach us. What lies beyond is permanently sealed off. But here's where the story turns. Because the cosmic horizon, the edge of what light has had time to reach, might not be the only kind of horizon. There's another boundary, deeper and stranger, that has nothing to do with light or time. It has to do with how the universe began, and whether it ever stopped beginning. In the first fraction of a second after the Big Bang, space didn't just expand, it inflated. For about 10 to the power of negative 32 seconds, the universe grew faster than anything inside it could possibly measure. A region smaller than an atom, bloated to the size of a galaxy, then kept going. That inflationary burst smoothed out the universe, erased any large-scale structure that might have existed before, and set the stage for everything that came after. But inflation doesn't have to stop everywhere at once. The theory that describes this process, eternal inflation, predicts that while inflation ended in some regions, giving birth to universes like ours, it continued in others. And in those regions, it's still going. Space is still doubling in size every fraction of a second, stretching and stretching without end. Occasionally, a patch of that inflating space stops inflating, and when it does, a new universe forms. A new Big Bang. A new bubble. Our universe is one of those bubbles. And the space between bubbles, it's still inflating. Faster than light. Faster than anything. Which means we're not just inside an observable bubble 46.5 billion light-years wide. We're inside a universe bubble floating in an eternally inflating space that's giving birth to new universe bubbles every moment. Billions of them, each one causally disconnected from the others, each one with its own Big Bang, its own galaxies, its own structure. And here's the strangest part, those other bubbles don't have to obey the same laws we do, because the thing that determines the laws of physics, the constants, the forces, the particles, is how space settles when inflation stops. Different stopping points lead to different physics. In some bubbles, gravity might be stronger. Stars would burn out in millions of years instead of billions. Galaxies would collapse into black holes almost immediately. In others, the electromagnetic force might be too weak to hold atoms together. No chemistry, no molecules, just loose clouds of particles drifting in the dark. Most bubbles are sterile, dead on arrival. The constants don't align in a way that allows complexity, let alone life. But in a multiverse with infinite bubbles, even the rarest combinations happen somewhere. And we're in one of the rare ones. Not because we're special, but because only the rare ones produce observers capable of asking why they're here. So when you look at that cosmic horizon, the edge of the observable universe, you're not looking at the edge of reality. You're looking at the edge of one bubble inside one patch of space, inside a structure that might have no edge at all. The question isn't how big the universe is anymore. The question is, which universe are you even asking about? Rewind to the beginning. Not the Big Bang, before that. Before space had structure, before time had meaning, before anything we'd recognize as matter existed. There was a field. Physicists call it the inflaton field, and it pervaded all of space. This field had energy, a lot of it, and that energy had a peculiar property. It made space itself expand, not gradually, the way the universe expands today, but exponentially, violently, space doubling in size every tiny fraction of a second. For 10 to the power of negative 32 seconds, this happened. That's a decimal point followed by 31 zeros and then a 3. A duration so short that calling it an instant is generous. But in that sliver of time, a region of space, smaller than a proton, expanded to something larger than our entire observable universe today. This is cosmic inflation. And it solved several major problems in cosmology. It explained why the universe looks the same in every direction, because everything we see came from a tiny uniform patch that got stretched. It explained why space is flat, because any curvature got ironed out by the expansion. It explained why we don't see magnetic monopoles or other exotic relics, because they were diluted to the point of invisibility. Inflation worked. The data supported it. By the early 2000s, most cosmologists accepted some version of inflation as part of the standard model. But then, someone asked a simple question: why did inflation stop? The answer, according to the math, is that the inflaton field decayed. It dropped from a high energy state to a lower energy state the way water freezes or steam condenses. When it decayed, the energy that had been driving inflation got converted into particles, quarks, electrons, photons. That's the Big Bang. The moment inflation stopped, a normal expansion began. But here's the problem. The inflaton field doesn't decay everywhere at once. Fields are quantum objects, which means they fluctuate. In some regions, the field decays early. Those regions stop inflating and form universes. But in other regions, the quantum fluctuations push the field back up to a higher energy state. Those regions keep inflating. And while they're inflating, they're expanding so fast that they generate more volume than the regions that stopped. The result is a runaway process. The parts of space that keep inflating grow faster than the parts that stop. So even though universes form constantly, the inflating regions always dominate. Inflation never globally stops. It just stops locally, creating pocket universes, bubbles, while the space between them continues to inflate forever. This is eternal inflation. And if it's correct, then the Big Bang wasn't a singular event. It's an event that happens over and over in different places at different times forever. Alan Guth, one of the founders of inflationary theory, described it this way: the multiverse is like boiling water. Bubbles form and rise to the surface, but the water never stops boiling. Our universe is one bubble. There are others, countless others, and they keep forming. In 2023, physicists at MIT published refined models of eternal inflation based on updated data from Planck and other surveys. The models showed that if inflation started at all, and the evidence strongly suggests it did, then eternal inflation is almost inevitable. The quantum fluctuations that keep some regions inflating are baked into the physics. You can't have inflation without them. Which means the multiverse isn't some speculative add-on. It's a prediction of the same theory that explains why our universe is flat and smooth. But there's a catch. The bubbles, the individual universes, can never interact. The space between them expands faster than light. If you tried to travel from one bubble to another, you'd be swimming against a current that's accelerating away from you at unimaginable speed. You'd never get there. No signal would ever get there. The bubbles are causally isolated, permanent islands. So, how do we know any of this is real? We don't directly. We can't observe other universes because they're beyond our horizon, not just the cosmic horizon, but a more fundamental horizon imposed by eternal inflation itself. But we can look for indirect evidence. One possibility is collisions. If our universe formed close enough to another bubble, and if the space between them was expanding slowly enough at that moment, the two bubbles might have touched before being pushed apart. The collision would leave a mark, a subtle pattern in the cosmic microwave background, like a bruise on the surface of spacetime. Physicists have looked for these bruises. So far, they haven't found any. But the absence of evidence isn't evidence of absence. The collision might have happened in a direction we haven't measured precisely enough. Or our bubble might have formed in a sparse region where collisions are rare. The other possibility is more philosophical. If eternal inflation is true, then the number of universes isn't just large, it's infinite. Every possible configuration of matter and energy that can exist does exist somewhere in the multiverse. There are universes where stars never formed, universes where galaxies are 1,000 times denser, universes where the cosmic microwave background is hotter, colder, or absent entirely. And there are universes almost identical to ours. Universes where Earth formed, where humans evolved, where you're listening to this exact sentence but with one neuron firing differently in your brain. Or where you made a different choice this morning. Or where a slightly different sperm fertilized the egg that became you, and someone almost like you but not quite is sitting where you are now. If the multiverse is infinite, then every possible version of history is real. Not metaphorically real, physically real, playing out in some distant bubble. That's difficult to process. It violates our intuition that we're unique, that our choices matter in some absolute sense. But in an infinite multiverse, uniqueness is impossible. everything happens. Every version of you exists. The only thing that makes this version significant is that it's the one you're experiencing. But even that strangeness pales compared to what comes next, because the bubbles don't just differ in their histories, they differ in their laws. The constants of nature, the strength of gravity, the mass of the electron, the speed of light aren't the same in every bubble. They can't be, because those constants are determined by how space settles when inflation stops and different bubbles settle in different ways. Which raises a question that sounds almost theological. Why does our universe have the constants it does? The answer might be that it doesn't matter, that we're just one bubble in a sea of 10 to the power of 500 possibilities. And the reason we're here to ask the question is because our bubble happened to roll the dice in a way that allows atoms, stars, and life. In most bubbles, the dice come up empty, but in an infinite multiverse, even the longest odds hit eventually. And that's where the story gets truly strange. Because if the laws of physics are different in other bubbles, then the word universe starts to lose meaning. What we call the universe, the thing with galaxies and stars and the Big Bang, is just one configuration, a local accident. And the deeper reality, the thing that contains all the bubbles, might not have galaxies or stars or anything we'd recognize. It might just be space inflating forever. So the cosmic horizon isn't the limit. The universe bubble isn't the limit. The limit, if there is one, is so far beyond our grasp that we don't even have the language to describe it. But we do have the math, and the math says 10 to the power of 500. In the late 1990s, string theory was the leading candidate for a theory of everything, a single mathematical framework that could unify gravity with the other forces of nature. The idea was elegant. Instead of treating particles as points, treat them as tiny vibrating strings. Different vibrations produce different particles. An electron is one kind of vibration, a quark is another, a photon is another. Everything emerges from the same underlying object. But string theory had a problem. It didn't predict one universe. It predicted many. The details are technical, but the core issue is this: string theory requires extra dimensions. Not the 3 spatial dimensions we experience, but 6 or 7 more curled up so small we can't perceive them. The way those extra dimensions curl their shape, their size, determines the constants of nature. Different shapes give you different physics, and there are a lot of possible shapes. In 2003, physicists Raphael Bousso and Joseph Polchinski calculated how many distinct configurations the extra dimensions could take. Their answer, roughly 10 to the power of 500. That's not a number you encounter in everyday life. It's not even a number you encounter in most of physics. To put it in perspective, the observable universe contains about 10 to the power of 80 atoms. The number of seconds since the Big Bang is about 10 to the power of 17. The number of Planck volumes, the smallest possible units of space that fit inside the observable universe, is about 10 to the power of 185. 10 to the power of 500 is bigger than all of those combined, raised to the power of themselves several times over. It's a number so large that if every atom in the universe represented a different configuration, you'd still be nowhere close. You'd need 10 to the power of 420 universes, each packed with atoms to represent all the possibilities. And each possibility corresponds to a different set of physical laws. In one configuration, the electron might be twice as heavy. In another, gravity might be 10 times stronger. In another, the electromagnetic force might barely exist. Every combination of constants that can arise from the geometry of the extra dimensions does arise somewhere in the landscape. This is the string landscape. And it's not a bug of string theory, it's a feature. Because if eternal inflation is true, then all of those configurations are real. Every time a bubble universe forms, the extra dimensions settle into one of the 10 to the power of 500 possible shapes. Most of those shapes produce universes that are hostile to complexity. But some produce universes like ours. The question is how many? In 2023, a team at Stanford ran simulations to estimate how many configurations in the string landscape could support stable atoms. Their conclusion: less than 1 in 10 to the power of 100. That means for every universe where chemistry is possible, there are 10 to the power of 100 universes where it isn't. And chemistry is just the first filter. You also need stars that live long enough to forge heavy elements. You need planets that can hold atmospheres. You need a universe old enough for complexity to develop. Each of those requirements narrows the range further. By the time you account for all the constraints, the fraction of universes that could support life is staggeringly small. Not zero, obviously not zero because we're here, but small enough that if you picked a random universe from the landscape, the odds of it being habitable are functionally nil. And yet, in an infinite multiverse, small probabilities don't matter. Even 1 in 10 to the power of 500 happens infinitely many times. Somewhere in the multiverse, there's a universe where gravity is slightly stronger than ours, but still weak enough for stars to burn slowly. Somewhere else, the electron is heavier but not so heavy that molecules fall apart. And somewhere against all odds, the constants align exactly as they do here. We're in one of those universes. Not because we're lucky, but because only those universes produce observers capable of noticing. This is the anthropic principle, and it's deeply unsatisfying to a lot of physicists because it replaces prediction with selection. Instead of explaining why the constants have the values they do, it says they have those values here because if they didn't, we wouldn't be here to ask. But the alternative is worse. The alternative is to believe that the constants are fine-tuned by coincidence, or by some mechanism we haven't discovered, or by design, and none of those options sit comfortably with the data. The data says the constants are what they are, and if you accept eternal inflation and the string landscape, the data also says there are 10 to the power of 500 other sets of constants playing out in 10 to the power of 500 other bubbles. Consider what that means. Every force, every particle, every interaction we've ever measured is local. The standard model of particle physics, the framework that describes quarks, leptons, bosons, and their interactions, is not a universal law. It's a local bylaw specific to our bubble. In another bubble, there might be 5 forces instead of 4, or 12, or 2. Particles we've never imagined might dominate. Symmetries we take for granted might be broken in completely different ways. And most of those universes would be unrecognizable, not just lifeless but structureless. In a universe where gravity is too strong, matter collapses into black holes almost immediately. No stars, no galaxies, just a seething mass of event horizons swallowing everything. In a universe where the strong nuclear force is too weak, atomic nuclei fall apart. Protons can't bind to neutrons. Hydrogen is the only element, and it doesn't stick around long. In a universe where the cosmological constant, the term that describes the energy of empty space, is too large, the universe tears itself apart before stars can form. Space expands so fast that matter never clumps together. No structure, no complexity, just diffuse gas cooling into nothing. These aren't hypothetical disasters. They're the default outcome for most configurations in the landscape. Our universe, with its stable atoms and long-lived stars, is a rare exception. But here's the twist. Rare doesn't mean special. In an infinite multiverse, rare things happen infinitely often. There are infinitely many universes like ours. Infinitely many, where stars form, where planets cool, where life eventually crawls out of the oceans and starts asking questions. And there are infinitely many universes almost like ours. Universes where the electron is 1% heavier and chemistry works slightly differently and evolution takes a different path. Universes where humans never evolved but something else did. Universes where intelligence arose on a moon instead of a planet, or in the atmosphere of a gas giant, or in the cold depths of an ice-covered ocean. The multiverse doesn't just contain every possible universe. It contains every possible version of every possible universe. Every branch, every variation, every alternate history. And we're in one of them. One configuration, one set of constants, one random point in a landscape so vast that the word vast is almost meaningless. So why these constants? Why this universe? There's no answer to that question. Or rather, the answer is no reason. The constants are what they are here because they had to be something, and this is what they are. In another bubble, they're different. And in another, different again. The multiverse doesn't care about our constants any more than the ocean cares about one particular wave. But it does raise a darker question. If our universe is just one bubble among 10 to the power of 500, and if the vast majority of those bubbles are sterile or hostile, then what are the odds that we're living in the most stable configuration? What if we're not? What if our universe is only metastable, stable enough to last for billions of years but not truly stable? What if there's a lower energy state the universe could fall into, and the only thing keeping us here is a quantum barrier that could break at any moment? That possibility is real, and it has a name. But before we get there, there's something stranger to consider. Because even if the multiverse has 10 to the power of 500 bubbles, each with its own laws that still assume space has 3 dimensions, what if it doesn't? In the 1970s, a physicist named Jacob Bekenstein was studying black holes. Specifically, he was trying to understand their entropy, a measure of disorder, or more precisely, the number of possible internal states a system can have. Classical black holes shouldn't have entropy. They're defined entirely by 3 numbers: mass, charge, and spin. Everything else, the details of what fell in the structure of the matter, the history is erased. A black hole made from collapsing stars looks the same as a black hole made from compressed hydrogen as long as the 3 numbers match. But Bekenstein realized that if black holes have no entropy, they violate the second law of thermodynamics. Throw a hot object into a black hole, and its entropy disappears. The total entropy of the universe decreases, which shouldn't be possible. So Bekenstein proposed that black holes do have entropy, and he calculated how much. The answer depended on the surface area of the event horizon, the boundary beyond which nothing can escape. Not the volume, the area. That was strange. Entropy usually scales with volume. A box twice as big holds twice as many particles and has twice as much entropy. But for black holes, the entropy is proportional to the surface area, not the interior volume. Stephen Hawking refined Bekenstein's calculation and confirmed it. Black hole entropy is exactly 1/4 of the event horizon's area measured in Planck units. The result is now called the Bekenstein-Hawking entropy, and it's one of the most solid results in theoretical physics. But it implies something deeply weird. If entropy measures the number of possible states, and if a black hole's entropy depends on its surface area, then all the information about what's inside the black hole must somehow be encoded on the surface, not in the volume, on the surface. In the 1990s, physicist Gerard Hooft and later Leonard Susskind took this idea seriously. They proposed the holographic principle. The information content of any region of space is not determined by its volume, but by the area of its boundary. It's called holographic because it works like a hologram. A hologram is a 2-dimensional surface that encodes a 3-dimensional image. When you look at a holographic credit card, you see depth and structure, but all the information is actually stored in a flat film. The 3-dimensional image is a projection. The holographic principle says the universe works the same way. Everything inside a region of space, every particle, every field, every interaction can be encoded on the boundary of that region. And what we experience as 3-dimensional reality is, in some sense, a projection from that 2-dimensional encoding. This sounds like philosophy. But in 1997, physicist Juan Maldacena found a concrete example. He showed that a specific 5-dimensional universe, a space called anti-de Sitter space, is mathematically equivalent to a 4-dimensional quantum field theory on its boundary. Every event in the 5-dimensional interior corresponds to a process in the 4-dimensional boundary, and vice versa. The interior and the boundary are not separate things. They're 2 descriptions of the same physics. One description uses 5 dimensions, the other uses 4, but they contain the exact same information. This result, called the ADS-CFT correspondence, is one of the most important discoveries in theoretical physics in the last 30 years. It's been tested in thousands of calculations, and it works. The 5-dimensional space and the 4-dimensional boundary are truly equivalent, which raises an uncomfortable question. If a 5-dimensional universe can be described by a 4-dimensional boundary, could our 3-dimensional universe be described by a 2-dimensional boundary? The answer, according to the holographic principle, is yes. In fact, it has to be. Because the principle isn't specific to black holes or anti-de Sitter space. It's a general statement about how information is stored in spacetime. Every cubic meter of space can hold a maximum amount of information. That maximum is determined by the surface area of the region, not its volume. For a region 1 meter on each side, the maximum information is about 10 to the power of 69 bits. That sounds like a lot, but it's far less than what you'd expect if information scaled with volume. If information scaled with volume, a cubic meter could hold about 10 to the power of 105 bits. But it can't. The universe doesn't allow it. The boundary sets the limit. So where is that boundary? If our universe is holographic, where is the two-dimensional surface that encodes everything? One possibility is the cosmic horizon. The edge of the observable universe 46.5 billion light-years away might be the boundary. Everything inside, every star, every galaxy, every atom might be encoded on that distant surface. And what we experience as three-dimensional space is a projection inward. But this isn't just a mathematical curiosity. It has real consequences. If the universe is holographic, then the number of possible states the universe can have is finite. Not just practically finite, but fundamentally finite. You can count them. And the count depends on the area of the cosmic horizon. For the observable universe, that number is about 10 to the power of 120. That's the total number of distinct configurations all the matter and energy in the observable universe can take. Every possible arrangement of particles, every possible history, every possible outcome, all of it fits within 10 to the power of 120 states. Which means the universe, despite its appearance of infinite possibility, is discrete. There are only so many ways things can be. Once you've exhausted those 10 to the power of 120 configurations, you start repeating. And if the universe is infinite, or if the multiverse is infinite, then somewhere out there, far beyond any horizon, there's a region of space in exactly the same configuration as ours. Same galaxies, same stars, same Earth, same you. Not a copy, not a simulation, the same configuration arrived at independently. The holographic principle also suggests something stranger. If three-dimensional space is a projection from a two-dimensional boundary, then the dimensions we experience might not be fundamental. They might be emergent, a kind of illusion generated by the underlying two-dimensional physics. This isn't the same as saying space is fake. Space is real in the sense that we experience it and interact with it. But it might not be the deepest layer of reality. The deepest layer might be the boundary, and everything else, distance, volume, depth, might be derived from that. In 2023, researchers at Caltech published a paper exploring how quantum entanglement could generate space. Their idea is that entanglement, the strange quantum connection that links particles across distances, acts like the threads that weave space together. The more entangled two regions are, the closer together they appear. The less entangled, the farther apart. In this picture, space isn't a stage where physics happens. Space is what happens when quantum information gets organized in a certain way. The two-dimensional boundary contains the information, and entanglement between different parts of that information creates the illusion of three-dimensional space. If that's true, then the universe isn't made of space and time. It's made of information. And space and time are just ways that information arranges itself. It's difficult to hold that idea in your head without feeling unmoored, because it means the most basic features of reality, the fact that objects have locations, that distances are real, that you can move from here to there, are secondary. They're not built into the fabric of the universe. They emerge from something deeper. And that deeper layer might not have any of the properties we associate with reality. It might not have distance. It might not have time. It might not even have dimensions. It might just be information encoded on a surface, waiting to be read. Which brings us to a more radical possibility. If the universe is holographic, and if three-dimensional space is emergent, then maybe the two-dimensional boundary isn't the end of the story. Maybe there are more layers beneath that. More reductions, more projections, more boundaries. Maybe the two-dimensional surface is itself a projection from something one-dimensional. And maybe that one-dimensional structure is a projection from something even stranger, something that doesn't fit into our categories at all. Or maybe the layers go the other way. Maybe our three-dimensional universe is the boundary for a four-dimensional space, and that four-dimensional space is the boundary for a five-dimensional space, and so on up through dimensions we can't visualize or imagine. In that picture, we're not at the bottom, we're somewhere in the middle, looking down at projections of ourselves and up at the things projecting us. And the thing at the top, if there is a top, might be so far removed from our experience that calling it a universe is meaningless. But there's another option, even stranger. What if there is no fundamental layer? What if the holographic principle applies at every level forever? Projections of projections, boundaries of boundaries, with no final answer and no bedrock. Reality as an infinite regress. Information, encoding information, all the way down. That thought doesn't lead anywhere comfortable, but it's where the math seems to point. Space isn't what we think it is. Dimensions aren't fundamental, and the three-dimensional universe we inhabit might be nothing more than a shadow cast by something we'll never directly see. But even shadows have structure, and the structure of our shadow is strange enough, because the universe isn't just holographic, it's also higher dimensional. And those extra dimensions might not be curled up as small as string theory predicts. They might be close, very close. Close enough that another universe could be floating right next to ours, separated by a distance smaller than an atom but in a direction we can't point to. String theory doesn't just predict extra dimensions, it predicts exactly how many 11. One dimension of time, 3 dimensions of space that we experience, and 7 more spatial dimensions that are hidden. For decades, the assumption was that those 7 extra dimensions are curled up incredibly small on the order of the Planck length 10 to the power of -35 meters. At that scale, the dimensions would be invisible. We'd never interact with them directly. They'd only affect physics through subtle modifications to particle masses and forces. But in the late 1990s, physicists Lisa Randall and Raman Sundram asked a different question. What if some of those dimensions aren't small? What if they're large, even infinite, but we can't access them because we're stuck on a membrane? The idea works like this. Our three-dimensional universe is a membrane or brain for short floating in a higher dimensional space called the bulk. Everything we know, matter, light forces, is confined to the brain. We can move forward and backward, left and right, up and down, but we can't move in the other directions, the ones that lead off the brain into the bulk. Not because there's a wall, but because the particles we're made of are literally attached to the brain. Quarks, electrons, photons, they're all excitations of fields that live on the brain. They can't leave the same way a water wave can't leave the surface of a lake. But there's one exception, gravity. Gravity in this picture isn't confined to the brain. It propagates through the bulk. When you feel the pull of Earth's gravity, most of that force is traveling along the brain the way we'd expect. But some of it leaks off into the extra dimensions, spreading out in directions we can't follow. This solves a long-standing puzzle called the hierarchy problem. Gravity is absurdly weak compared to the other forces. The electromagnetic force between 2 protons is about 10 to the power of 36 times stronger than the gravitational force between them. Why? In the brain picture, it's because gravity dilutes. While the other forces stay concentrated on the brain, gravity spreads out through the bulk. By the time it reaches us, most of its strength has leaked away into dimensions we don't experience. But this also means something strange. If gravity leaks into the bulk, then gravity coming from the bulk could leak onto our brain. If there's another brain floating nearby in the bulk, another 3-dimensional universe with its own matter and galaxies, its gravity would affect us. Not strongly, because most of its gravity would stay on its brain just like ours, but weakly, like a faint pull from a direction that doesn't exist in our 3-dimensional space. Could we detect that? Possibly. If another brain is close enough, its gravitational influence might show up as an anomaly in how galaxies rotate, or how the cosmic microwave background fluctuates, or how particles behave in high-energy collisions. Physicists have looked. So far, they haven't found anything. But the searches are ongoing. And here's the strangest part, close doesn't mean what you think. 2 brains could be separated by less than a millimeter in the extra dimensions, and we'd never see the other brain. Not with light. Not with any electromagnetic signal, because light is confined to our brain. It can't cross the gap. Only gravity crosses. And gravity is weak, so the signal would be faint. But there's another possibility. If 2 brains collide, the energy released would be enormous, enough to trigger a new Big Bang. In fact, some versions of brain cosmology propose that the Big Bang wasn't the beginning of time, it was a collision between brains. Our universe formed in the impact zone, and the energy of the collision became the matter and radiation we see today. In this model, the Big Bang happens over and over whenever brains collide. Each collision creates a new three-dimensional universe filled with energy and expanding outward. And in between collisions, the brains drift through the bulk carried by whatever forces operate at that higher dimensional level. This is speculative, but it's consistent with the data, and it makes a testable prediction. If the Big Bang was a brain collision, the cosmic microwave background should show faint patterns left over from the impact. Ripples in space, like the ripples that spread when two objects collide in water. Researchers have searched the Planck satellite data for those ripples. The results are inconclusive. Some patterns hint at large-scale structure that doesn't quite fit standard inflation, but they could also be noise or artifacts of how the data was processed. We don't know yet. What we do know is that the extra dimensions, if they exist, are tightly constrained. The Large Hadron Collider has searched for signs of particles escaping into the bulk we can't access. So far, nothing. Which means if the extra dimensions are large, they're not that large, probably no bigger than a fraction of a millimeter. But a millimeter is huge compared to the Planck length. If the extra dimensions are even that size, it changes everything. It means the fundamental scale of physics, the scale at which quantum gravity becomes important, isn't 10 to the power of negative 35 meters. It's 10 to the power of negative 3 meters, 1,000 times closer to everyday scales. And if the extra dimensions are infinite, which some brain models allow, then the bulk is incomprehensibly large. Our brain could be a tiny sheet floating in an endless higher dimensional ocean surrounded by other brains, each one carrying its own universe. You can't visualize this. Our brains don't have the machinery for it, but you can think about analogies. A two-dimensional creature living on a sheet of paper wouldn't be able to perceive a third dimension. If another sheet of paper floated a centimeter above the first sheet, the creature would never see it. The two sheets would be separate worlds invisible to each other, even though they're incredibly close. Now add 5 more dimensions. Our three-dimensional brain is like that sheet of paper floating in an 11-dimensional bulk. Other brains might be floating nearby just a millimeter away in a direction we can't point to, and we'd never know unless gravity gave them away. This raises a question: if there are other brains, do they have the same laws of physics, or do the laws change from brain to brain? The answer depends on what determines the laws. If the laws are set by how the extra dimensions curl up on each brain, then different brains could have different laws. One brain might have strong gravity and weak electromagnetism. Another might have different particle masses. Another might not have atoms at all, just free quarks and gluons never binding into anything stable. In that case, the multiverse isn't just a collection of bubble universes separated by inflating space. It's also a collection of brains separated by extra dimensions, and each brain might host its own version of the multiverse, its own set of bubble universes, each with slightly different constants. Multiverses within multiverses stacked in dimensions we can't see. And if the bulk itself is dynamic, if it can expand, contract, or warp, then the brains might move. They might drift closer together or farther apart. They might collide, triggering new Big Bangs. They might merge, combining two universes into one. All of this is possible within the framework of string theory and brain cosmology. None of it is proven, but none of it is ruled out either, which leaves us in a strange place. We know our universe has 3 spatial dimensions. We know those dimensions are expanding. We know the universe is full of matter and energy distributed in a way that matches the predictions of inflation and general relativity. But we don't know if the 3 dimensions are all there is. We don't know if we're confined to a brain or if the extra dimensions are just too small to see. We don't know if other brains exist or if we're alone in the bulk. And we don't know if the bulk itself is the final layer or if it's embedded in something even larger. What we do know is that the picture of reality we grew up with, 3 dimensions of space, 1 dimension of time particles moving around inside, is incomplete. At best, it's a local approximation. At worst, it's a shadow on a wall, and the real structure is something we've barely begun to understand. And one of the truths the shadow reveals is this: the universe might not be made of matter and energy at all. It might be made of information, and information at its most fundamental level might behave like a computer program. In 2003, philosopher Nick Bostrom published a paper with a simple argument. If a civilization becomes advanced enough to build computers that can simulate conscious beings, and if that civilization has any interest in running such simulations, then the number of simulated consciousnesses will vastly outnumber real ones. The logic is straightforward. A sufficiently advanced civilization could run billions or trillions of simulations. Each simulation could contain billions of conscious entities. The ratio of simulated minds to real minds becomes astronomically large. And if you're a conscious being, the odds that you're one of the real ones rather than one of the simulated ones become vanishingly small. This is the simulation hypothesis. And while it sounds like science fiction, it's taken seriously by a non-trivial number of physicists and philosophers. Not because there's evidence for it, but because there's no clear way to rule it out. The universe does have features that, if you squint, look like the constraints of a simulation. The speed of light acts like a frame rate, a maximum speed at which information can propagate. The Planck length acts like a resolution limit, a smallest possible unit of space below which the concept of distance breaks down. Quantum mechanics has a measurement problem. Particles don't have definite states until they're observed, which is reminiscent of a program that only renders details when necessary. None of this is proof, but it's enough to keep the idea alive. In 2024, a team at MIT explored whether there are ways to test the simulation hypothesis. Their conclusion, probably not. A sufficiently advanced simulation would be indistinguishable from reality. Any anomaly we detected could be explained as a feature of the underlying physics, not a bug in the code. And if the simulators wanted to hide evidence of the simulation, they could patch any inconsistencies before we noticed them. But there's a deeper issue. Even if we are in a simulation that doesn't answer the fundamental question, it just pushes it back one level. Where did the simulators come from? Are they in a simulation too? And if not, what kind of universe do they inhabit? If their universe is also governed by laws of physics, then we haven't escaped the problem we've just relocated. And if their universe isn't governed by laws, then what does that even mean? The simulation hypothesis doesn't solve the mystery of existence. It reframes it. But the reframing does highlight something important. Reality, at its deepest level, might be computational. Not in the sense that it's running on a computer, but in the sense that it's structured like one. Information in, information out. Rules applied consistently. States updated in discrete steps. And if reality is computational, then it has limits. Not practical limits, but fundamental ones. There's only so much information space can hold. Only so many states matter and energy can take. Only so many ways the universe can evolve. Those limits aren't arbitrary. They're built into the structure of space-time itself. At the smallest scales, space doesn't behave like a smooth continuum. It behaves like a foam. This is quantum foam, and it's one of the least intuitive concepts in physics. But it's also one of the most important. The idea comes from combining quantum mechanics with general relativity. In quantum mechanics, everything fluctuates. Particles appear and disappear. Energy spikes and drops. Nothing is stable at short timescales. In general relativity, space-time itself is dynamic. It curves, stretches, and warps in response to matter and energy. Put those two ideas together, and you get a picture of space-time at the Planck scale. 10 to the power of negative 35 meters and 10 to the power of negative 43 seconds, where space and time are constantly fluctuating. Tiny wormholes open and close. Virtual particles pop in and out of existence. The geometry of space writhes and churns, never settling into a smooth configuration. This is quantum foam, and it's not just a theoretical curiosity. It's a prediction of any theory that tries to merge quantum mechanics and gravity. Different theories predict different details of the foam, but they all agree on the basic picture. At the smallest scales, space is chaotic. What does that chaos look like? We can't observe it directly. The Planck scale is 20 orders of magnitude smaller than a proton. No microscope will ever resolve it. No particle accelerator will ever probe it. The energies required are beyond anything we can produce. But we can calculate what should happen. And the calculations say that space-time at the Planck scale is a seething mass of geometry. Not just curved, but fractured. Not just dynamic, but turbulent. In some sense, the Planck scale is where space and time stop being meaningful concepts. Below that threshold, you can't say a particle is here or there because here and there are fluctuating too fast to define. You can't say an event happens now or then because now and then are dissolving into quantum uncertainty. The smooth spacetime we experience at macroscopic scales is an average, a statistical calm that emerges when you zoom out from the microscopic chaos, like the surface of the ocean smooth from an airplane but choppy and turbulent up close. And just as the ocean is made of water molecules, spacetime might be made of something. Discrete units smaller than the Planck length that combine to create the illusion of continuity. Or perhaps spacetime isn't made of anything. Perhaps it's an emergent phenomenon arising from deeper quantum processes that don't involve space or time at all. This connects back to the holographic principle. If spacetime is emergent and if the information content of a region is determined by its boundary area, then the quantum foam might not be fundamental either. It might be a projection like the three-dimensional universe is a projection from a two-dimensional boundary. In that picture, the Planck scale isn't the bottom, it's just another layer. And beneath it, there's something else. Something that doesn't have the properties we associate with space or time. Something purely informational. What would that be like? We don't have the language to describe it. It's not a place. It's not a thing. It's not even a structure in the usual sense. It's just information arranged in some pattern following some rules generating everything we perceive as reality. If that's true, then the universe isn't made of particles or fields or space-time. It's made of bits. And the quantum foam is what happens when those bits interact at the smallest possible scales. This leads to a strange conclusion. If space-time is emergent, then the distinction between real and simulated starts to blur. Because if our universe is information processing information, then it's already computational. It's already running on rules. And whether those rules are fundamental laws of nature or lines of code in a simulation becomes a question without an answer. Both descriptions might be true, or both might be approximations of something deeper that we can't yet articulate. But here's what's clear: the universe at the Planck scale is not smooth. It's not solid. It's not even continuous. It's a foam, a froth, a bubbling chaos that only looks calm when you step back. And that calm is fragile, because the constants that keep the foam stable, the values that determine how strong gravity is, how fast the foam fluctuates, how much energy the vacuum contains, are finely balanced. Change any of them by a tiny amount, and the foam collapses, or explodes, or does something so strange we don't have a word for it. Which brings us to the most unsettling question of all. If the universe is balanced on such a delicate edge, how do we know it's stable? How do we know we're not sitting in a universe that looks stable but isn't? That's metastable, temporarily calm, but capable of falling into a lower energy state at any moment. And if that lower state exists, what happens when we fall into it? The cosmological constant is a number that describes the energy density of empty space. Einstein introduced it in 1917 as a way to keep the universe static, then abandoned it when observations showed the universe was expanding. For decades, physicists assumed the cosmological constant was zero. In 1998, two teams of astronomers measured the brightness of distant supernovae and discovered something unexpected. The expansion of the universe is accelerating. Galaxies aren't just moving apart, they're moving apart faster than they were a billion years ago. Something is pushing them. That something is dark energy. And the simplest explanation for dark energy is that the cosmological constant isn't zero. It's positive, but very, very small. How small? About 10 to the power of negative 122 in natural units. That's absurdly small. But here's the problem: quantum field theory predicts the cosmological constant should be much larger. Specifically, it should be about 1. Not 10 to the power of negative 122. Just 1. The discrepancy is 10 to the power of 122. That's the largest mismatch between theory and observation in the history of physics. If you wanted to build a model of the cosmological constant, and you predicted it would weigh as much as a grain of sand, but it actually weighed as much as the sun, you'd still be off by a factor of only 10 to the power of 30. The cosmological constant mismatch is 92 orders of magnitude worse than that. No one knows why the cosmological constant is so small. There's no mechanism in known physics that naturally produces a number that tiny. And yet it has to be that tiny. Because if it were much larger, the universe would have torn itself apart long before stars could form. Run the numbers. If the cosmological constant were 10 to the power of negative 120, instead of 10 to the power of negative 122, just 1% larger, the universe would have expanded so fast that matter never clumped together. No galaxies, no stars, no planets, just a thin gas cooling into oblivion. If the cosmological constant were negative, the universe would have collapsed, not in billions of years, but in thousands. Gravity would have overwhelmed the expansion, pulled everything back together, and crushed the universe into a singularity. The range in which the cosmological constant allows structure to form is staggeringly narrow. 1 part in 10 to the power of 120. That's like balancing a pencil on its tip, but the pencil is 1,000 kilometers tall and the tip is 1 atom wide. And the cosmological constant isn't the only finely tuned parameter. The strength of gravity is another. If gravity were just slightly stronger, stars would burn out in millions of years instead of billions. No time for complex chemistry. No time for life. If gravity was slightly weaker, stars wouldn't form at all. Hydrogen clouds would drift in space forever, never collapsing under their own weight. The strong nuclear force, the force that holds atomic nuclei together, is also finely tuned. If it were 2% weaker, deuterium wouldn't form. Without deuterium, stars couldn't fuse hydrogen into helium. No energy source, no heavy elements, no chemistry. If the strong force were 2% stronger, all the hydrogen in the early universe would have fused into helium immediately. No hydrogen left for stars. No water, no organic molecules. The electromagnetic force has the same problem. If it was slightly stronger, electrons would bind too tightly to nuclei, and chemical reactions would be too slow for life. If it was slightly weaker, atoms wouldn't hold together. Molecules would fall apart. The mass of the electron matters too. If electrons were 3 times heavier, atoms would collapse. If they were much lighter, chemistry would change in ways that make complex molecules impossible. And the list goes on. The ratio of the proton mass to the electron mass, the number of spatial dimensions, the amplitude of quantum fluctuations in the early universe. Every one of these parameters sits in a narrow range. Outside that range, the universe either doesn't last long enough for complexity or doesn't allow the structure's complexity requires. This is the fine-tuning problem. And it's not just a curiosity. It's one of the central puzzles in cosmology. Why are the constants what they are? Why do they fall in the narrow range that allows galaxies, stars, planets, and life? There are 3 possible answers. First, coincidence. The constants just happen to have those values, and there's no deeper reason. This answer is unsatisfying, but it's not impossible. Coincidences happen. The universe doesn't owe us an explanation. Second, design. The constants were chosen by something or someone to allow life. This answer is popular outside of physics, but it doesn't explain anything. Who chose the constants? Where did they come from? What kind of universe do they inhabit? Third, selection. The constants have the values they do because we're observing a universe where life is possible. This is the anthropic principle, and it only makes sense if there are many universes, each with different constants. In that case, the fine-tuning isn't mysterious, it's inevitable. Life only arises in universes where the constants allow it, and we're in one of those universes because we have to be. We couldn't exist anywhere else. If eternal inflation and the string landscape are correct, then the third answer is the right one. There are 10 to the power of 500 universes, each with different constants. Most of them are sterile, but in the ones that aren't, observers arise. And those observers look around and think how lucky we are. But it's not luck, it's selection bias. Still, even if we accept the anthropic principle, there's a lingering discomfort, because the constants don't just allow life, they allow a universe that lasts for billions of years, that produces heavy elements that remain stable over cosmological timescales. They allow a universe that's interesting. And that raises a darker question. Are we sure the universe is stable? The answer, based on measurements of the Higgs boson mass, is no. In 2012, the Large Hadron Collider discovered the Higgs boson. Its mass is 125 giga-electron volts. That number is important because it determines the shape of the Higgs field, the field that gives particles their mass, and the shape of that field determines whether the universe is stable. Run the calculations and you find that the Higgs field is sitting in what's called a false vacuum. The field has energy, but it's not in the lowest possible energy state. There's a deeper valley, a true vacuum with lower energy. The Higgs field is sitting on a hill, not at the bottom of the hill. This is called a metastable state. It's stable in the sense that the field won't spontaneously roll down the hill under normal conditions. But it's not truly stable. A quantum fluctuation, a random jitter in the field, could nudge it over the edge. And if that happens, the field starts rolling toward the true vacuum. Once it starts, it doesn't stop. A bubble of true vacuum forms, and the bubble expands at the speed of light. Inside the bubble, the Higgs field has a different value. That means particles have different masses. Atoms don't hold together the same way. Chemistry changes. Stars collapse. Galaxies disintegrate. Everything inside the bubble is destroyed, not in the sense of being blown apart, but in the sense of ceasing to exist in any recognizable form. The laws of physics change, and the structures those laws created, atoms, molecules, stars, planets, you stop being stable. This is called vacuum decay, and it's not science fiction. It's a real possibility predicted by the standard model of particle physics. How likely is it? No one knows. The calculations involve quantum field theory at energy scales. We can't probe experimentally, so the uncertainties are large. But the current best estimate is that the probability of vacuum decay in any given cubic light year per year is absurdly low. Low enough that the universe should last for 10 to the power of 100 years or more. But here's the unsettling part. If vacuum decay happens anywhere, it happens everywhere. Because the bubble of true vacuum expands at the speed of light. Once it starts, there's no stopping it. It spreads across the universe, consuming everything in its path. You wouldn't see it coming. The bubble moves at the speed of light, so the first signal you'd receive, the first indication that anything was wrong, is the wave of destruction itself. One moment you're sitting here listening to this, the next moment gone. And it could be happening right now. A bubble of true vacuum could have formed 1 billion light years away 1 billion years ago, and it's racing toward us. No warning, no defense. That's the knife edge. The constants aren't just finely tuned to allow life. They're finely tuned to keep the universe from destroying itself, and the margin is razor thin. If the Higgs mass was slightly different, just a few giga-electron volts higher or lower, the vacuum would be stable. But it's not. It's metastable. And metastable means vulnerable. So why hasn't vacuum decay happened yet? If the universe is metastable, and if quantum fluctuations happen constantly, shouldn't the vacuum have decayed long ago? Maybe it has. Maybe we're living in a universe that's already decaying and the bubble just hasn't reached us yet. Or maybe the probability is so low that vacuum decay hasn't happened anywhere in the observable universe. Or maybe there's some mechanism we don't understand that prevents decay, some new physics at higher energies that stabilizes the vacuum. We don't know. And that uncertainty is part of the discomfort. The universe looks stable, but the data says it might not be. It might be balanced on the edge of a cliff, held in place by nothing more than quantum probability. And if the multiverse is real, then somewhere in some other bubble vacuum decay has already happened. Other universes have fallen into the true vacuum, and whatever was there is gone. We're still here. For now, but the knife edge is real, and the question isn't whether the universe will fall. The question is when. Or maybe the better question is, why are we on the knife edge at all? Why is the universe metastable instead of stable or unstable? And the only answer anyone has is because we happen to be in a universe where that's the case. In the multiverse, every possible configuration exists, including the ones that are metastable. And metastable universes last long enough for observers to arise and notice the fine-tuning. It's not comforting, but it's consistent with everything we know. Which leaves one last question. If the universe is one bubble in a multiverse, if the constants are finely tuned because we're in a rare configuration, if the whole structure is held together by nothing more than probability and selection, then what is all of this? What is a multiverse where reality splits into 10 to the power of 500 branches, where space might be a hologram, where dimensions fold and unfold, where the vacuum itself is unstable? What do you call that? We started with a number, 93 billion light years. The radius of the observable universe, a sphere of space and time containing everything we've ever seen or will ever see, 2 trillion galaxies, 100 billion trillion stars, more planets than we can count. And then we learned that sphere might be less than 1% of the actual universe. Maybe less than 1/400th. Maybe 0% if the universe is infinite. And then we learned the universe itself might be just one bubble in a foam that never stops forming. A multiverse where new universes are born every instant, each one causally cut off from the others, each one expanding and evolving in isolation. And then we learned those universes don't have to obey the same laws. The constants can change. Gravity can be stronger or weaker. Particles can have different masses. Some universes allow atoms, most don't. And then we learned that our three-dimensional space might be a projection from a two-dimensional boundary, that the volume we experience is an illusion, and the real information is encoded on a surface we'll never see. And then we learned that space might have more than 3 dimensions, that our universe might be a membrane floating in an 11-dimensional bulk, surrounded by other membranes, other universes separated by distances smaller than an atom but in directions we can't point to. And then we learned that space itself at the smallest scales isn't smooth. It's a quantum foam seething with fluctuations constantly creating and destroying tiny geometries that exist for less than the blink of an eye. And then we learned that the constants holding all of this together are finely tuned, not just a little, to 1 part in 10 to the power of 120, and that, if any of them was slightly different, the universe would collapse, or tear itself apart, or never form structure in the first place. And then we learned that even with the constants we have, the universe might not be stable. It might be metastable, sitting in a false vacuum, vulnerable to a quantum fluctuation that could trigger a cascade of destruction spreading at the speed of light. So what is all of this? We don't have a word for it. Universe is too small. Multiverse assumes too much. Reality feels inadequate, when reality itself might be layered, projected, emergent, computational, higher dimensional, and unstable all at once. But we can say a few things. First, scale is deceptive. The observable universe feels vast because we're small, but in the context of what might actually exist, it's a rounding error. A speck. A single bubble in a foam that extends forever. We've built telescopes that can see back to the first galaxies, traced the evolution of structure across billions of years, and mapped the cosmic microwave background to exquisite precision. And all of that, every observation, every measurement, every discovery is local. It's one patch of space, in one bubble, in one possible configuration of physics. Second, the laws we've discovered aren't universal. They're local bylaws. Gravity, electromagnetism, the strong and weak nuclear forces, they're the way physics works here. In another bubble, the rules might be different. In most bubbles, the rules don't allow complexity. But in a multiverse with 10 to the power of 500 branches, the rare cases happen infinitely often. Third dimensions are slippery. We experience 3 spatial dimensions because that's how our brains are wired and how the particles we're made of behave. But the math allows for more. And if string theory is right, those extra dimensions exist either curled up, small, or extended in a direction we can't access. Our 3-dimensional universe might be embedded in something larger, or it might be a projection from something smaller, or both. Fourth, space and time might not be fundamental. They might emerge from something deeper: information, entanglement, quantum processes that don't require a stage to play out on. In that picture, the universe isn't made of stuff. It's made of relationships, patterns, rules. And space is just the way those patterns organize themselves. Fifth, stability is fragile. The constants are finely tuned. The vacuum is metastable. The structure we see, galaxies, stars, planets, exists because a long chain of unlikely conditions held, change one link, and the chain breaks. In the multiverse, most chains break. We're in one that didn't. Not because we're special, but because broken chains don't produce observers. And sixth, we're at the edge of what we can know. Not because we lack the tools or the intelligence, but because the universe has horizons. Light only travels so fast. Space expands. Information gets trapped behind boundaries we can't cross. We've mapped the observable universe. We've inferred the existence of dark matter and dark energy. We've detected gravitational waves and measured the cosmic microwave background. But there are things we'll never measure, regions of space we'll never see, universes we'll never contact, dimensions we'll never access. The edge of the observable universe isn't a wall, it's a horizon. And beyond it, reality continues. But we're not part of that continuation. We're here in this bubble, with these constants, in this configuration. And everything we know is shaped by that fact. So when you look up at the night sky, what are you seeing? You're seeing photons that traveled for billions of years across expanding space to reach your eyes. You're seeing galaxies that formed when the universe was young that are now billions of light years away, receding faster than light can chase them. You're seeing the visible edge of a structure so large that the word large stops meaning anything. But you're not seeing the multiverse. You're not seeing the other bubbles. You're not seeing the extra dimensions, or the holographic boundary, or the quantum foam. You're not seeing the string landscape, or the brane collisions, or the inflating space between universes. You're seeing one narrow slice of reality filtered through the limitations of light and time, and the particular way your eyes and brain process information. It's a beautiful slice, a meaningful slice, but it's not the whole picture. And maybe that's okay, because even a narrow slice of reality is overwhelming. Even the observable universe, the part we can see and measure and map, contains more stars than we can count, more complexity than we can fully understand, more beauty and strangeness than we can absorb in a lifetime. We're small, the universe is large, and the universe might be embedded in the multiverse, the bulk, the quantum foam, the holographic projection, whatever it is larger still. But smallness doesn't mean insignificance, because we're the part of the universe that can look back at itself and ask what it is. We're the part that builds telescopes and runs experiments and writes equations and wonders. We're the part that can hold the idea of 10 to the power of 500 universes in our heads, even if we'll never visit them. And maybe that's the point. Not that we're at the center, not that we're special, but that we're here briefly in a universe that allows us to be here. In a bubble that formed when inflation stopped, in a configuration where the constants align, on a planet that cooled with an atmosphere that held with a star that burned steadily with a galaxy that doesn't collapse into a black hole. We're not the only ones. In an infinite multiverse, there are infinite versions of this moment playing out in infinite bubbles. But this version is ours. This bubble, this configuration, this narrow slice of an unimaginably large structure. And for now, it's enough to know it's there. To know that the observable universe is not the universe. That the universe is not the multiverse. That dimensions fold and unfold. That space might be a projection, that the constants are balanced on a knife edge, that reality is stranger and larger and more layered than we ever imagined. You won't see it from here. You'll only see the stars, but the stars are part of it. And so are you. The universe is larger than we thought. The multiverse is larger than we can think. And somewhere in all of that is an answer to the question, why is there something instead of nothing? We don't have that answer yet. We might never have it, but we're looking. And the looking itself is part of the story. The night sky is full of light. Most of it is old light that left its source billions of years ago when the universe was younger and smaller and stranger. Some of that light comes from galaxies that no longer exist in the form they had when the light was emitted. Some comes from galaxies that are now beyond the horizon, forever unreachable. But the light is here, and we can see it, and we can follow it back through time, through space, through the layers of reality, until we reach the edge of what's knowable. And then we stop. Not because the universe stops, but because we've reached the limits of our vision. Beyond that, the universe continues. The multiverse unfolds. The bubbles form and expand. The dimensions curl and stretch. The constants shift. The foam churns. And all of it, every bubble, every dimension, every configuration is part of the same incomprehensible whole. We call it reality. But we're only seeing a fragment. And even the fragment is enough to make us wonder,